Hello everybody, and welcome back to another video on the channel. If you saw my last videos, you realized that I was pretty busy. I had to go away from YouTube for a little bit, but I came back and I decided to upload 5 videos this time just to make up for the time that I've missed. And in those 5 videos, I finished my Intro to Calculus series, and I finished the final 4 videos of my Advanced Trigonometry/Geometry series. So now, you know it, it's time for arguably one of my favorite series of all time, the Calculus series. And what better way to start it is by explaining the power rule of differentiation, which is probably the first thing everybody learns as soon as they start learning calculus, assuming they already know what limits are. Before we go into the power rule itself, we have to learn a little bit of mathematical notation. So there are 2 main types of notation for derivatives. There's derivative notation, I believe it's also called Leibniz notation, and there is prime notation. Derivative notation, or Leibniz notation, as I think it is d over dx. It means derivative with respect to x. So if we have something like dy over dx, this means derivative of y with respect to x instead of just any derivative with respect to x. And prime notation is f, but then you have a prime or an apostrophe of x, which also that means the derivative of x. So f dash of x and d of f of x over dx is the exact same thing. They will be used interchangeably, but I just wanted to make sure you knew that. And then, of course, function notation, f of x represents a function of x. Now, a quick example is d over dx is basically x cubed is equal to f dash x, that's derivative of f of x, where f of x is equal to x cubed, and that's equal to 3x squared. What is the power rule exactly? It's a rule for differentiating any polynomial function. So any function of the form f of x is equal to x to the power of n. Now it can also be a times x to the m or anything after that. And those are a few identities that come with differentiation, but those will be explained in our next video. But for now, these are pretty much strict polynomials, or just one term. Not polynomials, not monomials with just one power. So d by dx, or the derivative with respect to x of x to the power of n, is equal to n times x to the power of n minus 1. Sometimes people will say it as bring down the exponent and subtract 1 from the power. By bring down, we mean multiply the rest by the exponent. There were 2 main discoverers of the power rule. So the 2 discoverers was Isaac Newton and Gottfried Wilhelm Leibniz, which also I think created the Leibniz notation. And both of these actually did it independently, so they didn't work together at all. And both of these was during the mid-17th century, less than 10 years apart from each other. So Newton's approach was to define it using something called fluxions. And fluxions are sort of like the instantaneous rate of change at a single point, which kind of explains derivatives at that same point. And Leibniz's approach uses differentials, basically intervals that are extremely tiny deviations from the original value to again find the derivative. This slide is just another recap, but what it is basically is it's explaining each of the steps in order. First, we have to identify the exponent. Then we need to multiply the formula by the exponent, and then reduce the exponent by 1. Example, x cubed becomes 3x squared. Now, the reason I decided to include this slide was to kind of break it down step by step and also give you a full kind of breakdown of everything that's involved inside this instead of just plugging and chugging a formula. It actually shows you the different steps you can take. But of course, plugging and chugging the formula is much faster. They're solved over here. I won't really be explaining them, but I will be explaining some examples a little later. So d by dx of x squared is 2 times x to the first, which is 2x. Example 2, we have 3x squared. Example 3, we have 5x to the power of 4. And for the final example, or example 4, we have x. Then what we have is 1, then times x to the power of 0, which of course is equal to 1, as x to the power of 0 is 1, and 1 times 1 is 1. Here are a few more examples, and I call this extended applications because the power rule works for all real exponents. So whether it be 15, 0.3, 85.1852153, negative 85.1852853, and so on, every real exponent from negative infinity to infinity, all of them work with the power rule. With complex exponents, however, it becomes a little different. And speaking of complex, here are a few more difficult examples involving fractions and slightly larger numbers. Of course, but all of them still use the same philosophy or the same power rule. So that's what makes it such a good rule, as it's super simple and easy to understand, but it's used in a ton, and I mean a ton of problems. Pretty much every problem will have some form of the power rule. Now, there are also a few real-world applications in physics, engineering, and economics. Physics is calculating velocity and acceleration. Engineering, optimization problems. Related rates is also something that could use power rules, but that's also more of something within calculus itself and less of physics and engineering. And in economics, it's marginal costs and revenue functions. But here are a few common mistakes to avoid. There are 3 main mistakes I saw. Mainly I've seen people do, or just in any problem. I've done these mistakes a lot myself when I was learning this. But before we go into the mistakes, I'd like to say this reminder: always check your work. Double check it, triple check it, quadruple check it. There is pretty much no worse feeling. Well, there are a few, but it's a really bad feeling, and also it's kind of a waste of any effort you put into the problem, that if you didn't check your work and you end up getting something wrong because of it. Now, the 3 main common mistakes are: number 1, forgetting to reduce the exponent; number 2, not bringing down the coefficient; and number 3, a small confusion with negative exponents. So maybe you might thought it was positive or negative, or maybe subtracting 1 made it negative, but you thought it was positive. That's happened a lot, and it's very, very annoying to deal with, as sometimes they're super tricky to spot because you're trying to finish a problem quickly, and you tend to overlook this. And then when you look back, you're like, where is it? Because you're frantically searching, because you're worried that why did you get the easiest problem on the test wrong? But sometimes they're also very easy to spot, as in, if you don't bring down the coefficient and you look at the rule one time, you'll quickly realize what you did wrong. Now, let's actually do a few practice problems. The first practice problem is to find the derivative of f of x is equal to x to the power of 6. Now, what we're going to do is we're going to quickly use the power rule and then, of course, go on to the solution. If you don't want to wait for me to explain this problem, and if you've already solved it, which I would probably do by pausing the video and doing it on your own, you can, of course, skip straight to the solution slide, where I quickly recount the steps and show the solution on a separate slide just for you guys who already know the concept and are just using most of the problems over here for practice. Now, the first thing that we need to do is, for now, we'll state the power rule. So, d by dx of x to the power of n is equal to n times x to the power of n minus 1. Now, what this is the power rule, of course, and then what we're going to do is we're going to pretty much plug and chug. So this is equal to, this becomes, because we have to plug it in, n, which in over here is 6, then x to the power of 6 minus 1. Now, if you simplify this, this becomes 6x to the power of 5. And that's about all there really is for this example. It's very simple. Here are all the steps explained right over here conveniently. So all we did is we did the formula and we plug and chug. That will mostly be what the examples are today, and after tomorrow's video, which explains a lot of the derivative identities and explains the formal proof behind the derivative using the limits definition of the derivative. That's a lot of derivatives in one sentence. But what's going to happen is a whole new world of possibilities is going to open up just by explaining those few identities. And that's essentially how we're going to roll from there. It's going to get harder and also sometimes even more interesting. And here we go. Here is the solution. F of x is equal to x to the power of 6. And f dash x is equal to 6x to the power of 5, where f dash x is, of course, the derivative of x. And on the bottom, here we go. Pretty simple. Using the power rule, n is equal to 6, and just plug and chug. Is to find the derivative of g of x is equal to 3x to the power of minus 2. Now, we are again going to state the power rule, so I won't delete that. But now we have a 3 on the outside, so we have to include that. Then multiplied by negative 2 over there, because we have to bring down the exponent. Then we have x power of negative 2 minus 1. So this is equal to negative 6 times x to the power of negative 3. Or it's also equal to negative 6 divided by x cubed. Whichever way you put it, I would personally put it this way, unless the problem specifically states to use only positive exponents. Then you must do it the second way, as if you do it the first way, you'll have a negative exponent, and it could be marked as wrong. So there you go, the power rule, plug and chug, but we also had a coefficient on the outside, so we just had to multiply that by the original value. The power rule with a coefficient, plug and chug, and the coefficient identity is actually where you have a coefficient, then you if you have a coefficient times a function, then you differentiate and you want to find the derivative, it's just the same coefficient times the derivative of that function. And that's one of the identities that will be covered tomorrow. And our third and final practice problem is to find the derivative of h of x is equal to x to the power of 3 over 4, where we're using a fractional exponent. I don't think it's really necessary to state the power rule anymore. If you still don't remember it, then of course feel free to look above or on the previous slides where I did show the power rule. So let's get started with the problem. Now, what we have to do is plug and chug. So we have 3 over 4 on the outside times x to the power of 3 over 4 minus 1. And this is going to be equal to 3 over 4 times x power of minus 1 over 4, as 3 over 4 minus 1 is minus 1 over 4. Now, if you want to only use positive exponents, you can do 3 divided by 4 times x to the power of 1 over 4, or even 3 divided by 4 times the 4th root of x, because if you have 1 by something, that means you have also the 4th. If you have x to the power of 1 by something, that means you have that nth root of x. Now I'm going to remove this definition, as for some reason over here it's clogging up. Or actually I'll just add it, never mind. Oh, there it goes, it works just fine. I don't know why it was there earlier, where the 4 was in fact touching the line that separates the numerator and the denominator. And here we go. Here's the solution. H dash of x is equal to 3 over 4 times x to the power of negative 1 over 4. And it's pretty much the same thing except we're using fractional exponents. And I think the main point of this lesson was to show you the formula and a few plug and chug examples. And here are a few key takeaways. It's a simple rule. The formula is right over there. It's universal application. It works for any real exponent. If you have an exponent of a complex number, it's much different. I mean, it's not too different, but it's pretty different. And it's very historically significant, as it's kind of like the first calculus, one of the first calculus rules that was invented or created and laid the foundation for some of the later rules in calculus. And the practical value is it's pretty much very essential for problem solving. And thank you so much for watching this video. I really hope you like, subscribe, and hit that notification button for more awesome videos just like this. Of course, if you liked it and if you thought my content was helpful, not trying to force anyone, you should only like, subscribe, and hit that notification button if you found real value from my videos, because that shows me that people find value from it and that I'm helping people understand more about math, which normally people think is very intimidating, but if you explain it enough and you do enough learning by doing, it's actually really good and efficient. So, thank you so much. See you in the next one. Please make sure to comment in case you have any suggestions or tips for future videos. And see you in the next one. Bye-bye.